Dear students, this is going to be our first lecture of Fourier analysis MTH 803. So the course is for integrated BSc MSc semester 8th. Now Fourier analysis is perhaps one of the most important developments in mathematics in say past 150 years or so, and it started with the study of heat equation by Fourier, the French mathematician. Jean-Baptiste Fourier, I think, is his complete name. As far as our course is concerned, it's very elementary. We are going to take baby steps towards the understanding of this Fourier analysis. And we are going to start with Fourier series. Now, before going to Fourier series, we can just recall what do we mean by the convergence of a sequence or a series of functions, right? So if you have a sequence of functions defined on some interval, let's call it AB. So I've got a sequence of functions, real valued functions for simplicity's sake. Then say let me explain it with the help of an example. Let my interval AB be 01 and my functions be the simple polynomials fn of x is equal to x raised power n. So I've got a countably many functions, a sequence of functions in which the first function is f1 of x, that is x, right? Then another function f2x would be x squared, and so on and so forth, right? So when I input a value from its domain 0, 1 into each of these functions, I get a sequence of numbers. Suppose I input the value 0, I will get a sequence of numbers 0, 0, so on and so forth. Suppose I input a value 1 by 2. So then I would get a sequence 1 by 2, 1 by 4, then you take the cube, that's 1 by 8, so on and so forth. Similarly, I can just input the values in the domain and I get sequences of numbers, and so on and so forth. I can input the value 1, then I will get 1, 1, 1, 1. I know I'm just revising what you've already done. Then if each of these sequences converge, which they do in this case, right? This is a constant sequence, it converges to 0. Of course, this is a powers of numbers less than 1, so it would also converge to 0, and this would converge to 1. In this way, I have got limits of the sequence of numbers when I input the value of the domain in the sequence of functions. Now in this way, since each of these, of course, when I input the value 0, it is determined by the function, the sequence of functions, right? Since they are, it depends upon my input what sequence of numbers I get. So I think, so these are fn of x's for different values of x. And since they depend upon x, so what I get in the end, these numbers, they all depend upon my input x. If my input is 0 in all the sequence of functions, if it is half in all the sequence of functions, then I get 0 and 0, and if the input is 1, I would get 1. So we can think of it as an f of x. They depend on x. This function that we got as a result of the convergence of the sequence of functions when we input the values of the domain, right? If I get, obviously it depends upon the domain. Suppose if I take x equal to 2, then this sequence would diverge. I will get 2, 4, of course 8, so on and so forth, and sequence would diverge. So leave that aside, but if in a given domain all the sequence of numbers that we get by inputting the value of the domain in the sequence of functions, if that happens, we call it pointwise convergence. And this limit, these set of values that I get for different values of x, I call it the pointwise limit function of f and x, right? So fx is basically just you just input the value of x. Of course it must converge, the right hand side must converge for each value of x. Only then this pointwise limit of this function makes sense, right? So then there is uniform convergence. Of course, first the convergence must be pointwise. Now if in this case, by the way, fx would be, as you can see, it would be 0. In case x lies between 0 and 1, it would be 1 in case x is equal to 1, right? So I've got a, by the way, this also shows you've got a sequence of continuous functions, polynomials, x square, x cube, and their pointwise limit in this domain, although convergent, but the function to which the sequence of function converges pointwise is not continuous, as you can see. Okay, leave that aside. Then if you recall, then you must have also learned in your earlier classes about uniform convergence of a sequence of functions. The uniform convergence is you've got first pointwise convergence. In addition to pointwise convergence, if we know what do we mean by convergence in that epsilon delta definition for convergence. When I say f and x converges for each x, right? So that means f and x minus fx, as you know, for any epsilon positive, there exists a natural number n. Okay, so if this happens for any epsilon, there exists such that this modulus is less than epsilon for all n bigger than or equal to n naught. Now since we are talking about here individual sequence of numbers, right? So this epsilon, this n naught, of course this always depends upon your epsilon. Your choice of epsilon would also always determine what n naught you should take. Again, this is something that you have done in your earlier courses in analysis, but this in our situation, this n naught would also depend upon our choice of x. Now in case it is independent of our choice of x within a certain domain, we say this sequence of functions converges uniformly to fx. Okay, now again I would advise you to revise that and go through that again. Uniform convergence over a certain domain of a sequence of functions. Now what does uniform convergence imply? Now one of the few things that emerge out of it is that if the convergence is uniform, if you have a sequence of continuous functions and the convergence is uniform over that domain, then the limit function would be continuous over that domain. Similarly, if you have another point is, okay, we can actually extend all these ideas to series, because what is a series? Series is basically the limit of the sequence of partial sums. If you have a series of functions, now f and x, and runs from 1 to infinity, f and x, suppose this is a series of functions, you mean accountably many functions which we add up for each value of x in a certain domain, which usually is an interval. Now we would say it would converge, or we write it is equal to Sx. It is a sum function. Then sum function is nothing but it is limit n approaches infinity Sn of x for each value of x. Again, all the rules apply. Now, and we know that what is Sn of x? Snx is the nth partial sum. I runs from 1 to n Si of x, right? Sorry, Fi of x. Okay, so if this sequence converges uniformly, we say this series converges uniformly. Again, uniformly means that epsilon delta definition that you are going to go through again, because we have to move ahead a little. It is just what you have done already. Okay, now again the question is, if you have, there are questions like these in uniform convergence. Suppose in the sequence of a series of functions, suppose you have a sequence or series of continuous functions. Is there sum again a continuous function, right? And furthermore, if you have a series or sequence of differentiable functions, is their limit function also a differentiable function? And further, you could also, can we differentiate term-wise? By that I mean, is d by dx, can I interchange this thing? Can I write it like this? Right? Okay, for this to be true, this is a little complicated, and there is a theorem which tells you when this would happen, but since we don't require this, but there could be another thing. If all the functions in the series are integrable, is the limit function integrable, or can we furthermore, can we integrate term by term. That means if you have a situation like this, all the functions are integrable. Is this true? The integral of the series, is it the same as series of the integrals of the functions, right? Since I would require this thing, this is obviously, this is, or not obviously, you have to prove it. Yeah, you must have proved it in your earlier classes, that this is true in case this, if you have each of these functions is integrable, and if the convergence to this convergence of the series of functions is uniform over the domain of integration, then this is true. You have a series of functions, and if each of them is integrable over a domain, say AB, then I can always interchange the operations of summation and integrating, summation and integration. Okay, so this is going to be basically what we are going to require here. And I also assume that you've done a course on Libby integration, although you must have heard about it, although it's not that important, frankly speaking. We are going to use it, but not that much. Okay, so that was our revision of what you have already done in your earlier classes. Now, in the case of Fourier series, we want to basically investigate this series. For the beginning, a series of this type. Let me write it as 1 by 2 a naught. A naught is some number plus summation n runs from 1 to infinity a n cos nx plus b sub n sin nx. So now, if I expand, why is this 1 by 2 a naught? Now that's a different story, but think of it just as a series. Now you've got a series of functions, so which is like a1 cos x plus b1 sin x plus a2 cos 2x plus b2 sin 2x, and so on and so forth. And of course, this is a series of functions in which we have got certain numbers, right? Now what we want to do, this is what we call a trigonometric series, obviously enough, huh? because trigonometric functions are involved, right? Now obviously the question is, what should be the restriction on these a_n's and b_n's so that this converges pointwise. And before going there, and how we are going to deal with this is that we first assume for the moment that suppose this converges to some function fx. Suppose this converges to fx, so that I can write fx is equal to this for all x belonging to, let me choose even an interval for simplicity's sake, although there is nothing special about this interval. We could use any interval. So the question is, the broader question in Fourier analysis, your Fourier series would be, what sorts of functions can be written like this as a sum of sines and cosines with certain numbers a1, a1, b2. Now we just flip the question. Suppose this is uniformly convergent. Suppose this is true, that fx is this function, this series converges uniformly to some function fx, a real valued function, for all x's in a certain interval, which for our convenience sake we take minus pi to pi. Okay, now if that is the case, if it converges, what is the relation of fx with these coefficients? Because cos x, cos 2x, sin 2x, we already know what they are. They are known trigonometric functions, which are unknowns. Now suppose this converges uniformly to this fx, how would these coefficients be related to fx? Now this relationship between these coefficients and this function fx is something really interesting, and something that is the starting point of our course. Okay, so keep this in mind. We have got this series of functions, right, which involves trigonometric functions and certain unknown numbers, right? And we want to think, suppose it does converge uniformly, over this interval, then what should be the relationship between this? How should fx and these unknown numbers a0, a1, b1, a2, b2 be related? Now, to derive that relation, we would need certain trigonometric certain formulas that you already know, which can be easily derived. Now let me write down them, and you are going to do them at home. I will do another easy to derive relations. That one is that minus pi to pi cos kx cos nx. If you integrate this from minus pi to pi, this is going to 0 for all kn running from 0, 1, 2, so on and so forth, provided that k is not equal to n. Right? Okay. Similarly, minus pi to pi, right? Cos square, that means, okay, let me write it as cos square nx. It would be the case when k is equal to n, because it is going to be 0 if k is not equal to n. But if k is equal to n, this would be pi for n running from 1, 2, so on and so forth, and this would be obviously 2 pi in case n is equal to 0, because if n is equal to 0, this is going to be 1, and you just integrate, what you get, 2 pi, right? Okay, similarly, minus pi to pi sine kx sine nx is equal to 0 for k n running from 1, 2, so on and so forth, k not equal to n. Remember that if we take any of them equal to 0, so here it does make sense, otherwise if you put that equal to 0, that's obviously going to be 0, so that won't be even required. And in case k is equal to n, by that I mean if I have to evaluate this integral minus pi to pi sine square nx dx, this would be equal to pi. Again, very easy to prove relations. And similarly, the last but not the least, minus pi to pi cos kx sine nx dx would always be equal to 0, kn running from 0, 1, 2, so on and so forth. Now put any values, whether they are equal or not. Here there is a difference. If they are equal, it's 0. If they are not equal, if they are equal, it's pi or 2 pi. If they are not equal, it's 0. Here, whether they are equal or not, if it is cos x and sin x, integral multiples of x, cos kx, cos nx, where kn are natural numbers, whole numbers basically, so it's going to be 0. So let's prove one here. Others, and also look at your study material that we have provided. So we can prove it with the help of trigonometric identities. Say I want to prove this, minus pi to pi, I want to prove the identity for this cos kx, cos nx dx. Okay. Now what I do, I use this trigonometric formula, as you already know, what that is cos of, if I take cos of kx plus nx, this is cos a plus b, so that would be cos kx cos nx minus sin kx sin nx, and similarly cos kx minus nx, that would be cos kx cos nx plus sin kx sin nx. And if you add them, so sine terms would go away, right? So you would basically get 1 by 2, let me write it, cos k plus n times x plus cos of k minus n times x is equal to twice because I've taken the 1 by 2 here. It would be cos kx cos nx. So if I substitute it here, I would get minus pi to pi cos kx cos nx dx is equal to, substituting this, it would be 1 by 2 into minus pi to pi cos of k plus nx dx, and I just split the integral, minus pi to pi cos of k minus n times x dx. And then, just integrate, very simple. So this would be 1 by 2, right, sine of k plus n x divided by k plus n, evaluated from minus pi to pi, plus 1 by 2 into, again, sine of k minus nx divided by k minus n, evaluated from minus pi to pi, right? Now we just substitute the value of pi. It's an integral multiple of pi. Sine at an integral multiple of pi is 0, and so is sine of minus pi. So everything is just 0. So this is 0 plus 0, that's equal to 0. So therefore this must be equal to 0, right? Of course, k cannot be equal to n because otherwise this is not defined. Okay? And other formulas that I wrote down are equally simple. Again, have a look at it. Okay, now having this in our kitty of these formulas of trigonometric functions, we can come to our question that if fx is equal to summation 1 by 2 a naught plus summation n runs from 1 to infinity a n cos nx plus bn sine of nx, this series, how is fx related to these coefficients? And I am saying that suppose f is indeed uniform. By that, when I say this is equal to this, I am saying that this converges uniformly to a function fx on the domain minus pi and pi. If that is the case, I want to evaluate these coefficients. Now I want to see how we can evaluate them, and actually we are going to evaluate them, right? Now what I do is, okay, first I just integrate them, right? We just integrate this function from minus pi to pi. So you would get 1 by 2, and since I am assuming that this is uniformly convergent, I can integrate this series on the right term-wise. I can integrate this one. I can take the integral inside the summation notation. So integral from minus pi to pi f of x dx, since I'm assuming uniform convergence, right, on the interval minus pi to pi, should be, because this is a constant, so this would be minus pi to pi of 1 dx plus summation n runs from 1 to infinity a n, again this is a constant, I take it away, so it's minus pi to pi cos nx dx plus integral minus pi to pi, of course I take chalo bn under rectangle, doesn't matter, I don't have place here, whatever. Okay, now this would be 1 by 2 a naught, of course this is just 2 pi, right, 1 integrate here, right, plus now look at this. So अगर इस इंटीग्रल को हम देखें तो क्या मिलेगा हमें, you will get basically sin nx divided by n, right, an तो यहाँ है ही, evaluated from summation भी है, everything whatever, and I have to evaluate from minus pi to pi. So integral multiple of anything, when I evaluate it would be sine of n pi, that is 0, sine of minus n pi, that's again 0, both and lower and upper values, right? Here I would have something like bn is out, so you integrate, so it would be minus cos nx divided by n, right? And I have to evaluate them from minus pi to pi. Now here what would happen, you can take minus bn out, n out, and inside we would have cos of n pi minus cos of minus n pi. Since they are the same, so this is again 0, this is again 0. What we are left at, we got something, so everything reduces to 0 here. So I would have 2 and 2 cancels out. So a naught should be then 1 by pi, I take this towards this, minus pi to pi f dx. So this is the value of a naught. Similarly, I can evaluate a n's and b n's. So now to evaluate a n's, what I do is I multiply both sides. Now I've got, remember I've got fx equal to, so let me write. So I've got this, fx is equal to this series, and the convergence is uniform, and I can do term by term integration over the domain minus pi to pi. Now fx, I just multiply both sides of this by cos, let me say cos kx, and then integrate. Okay, so okay, so what you will get is this. You multiply it by, or let me write first, just a change of notation, just to make things a little simpler. So I can write this also summation k runs from 1 to infinity, because in your notes there would be k, you might get confused. Ak, it's nothing different, right? Obviously you must know that, sine of kx. Okay, I just change the dummy variable. So fx, now I just multiply it by fx into cos nx. So you would get this is equal to 1 by 2 a naught into cos kx, sorry, cos nx. Then I would have plus summation n runs from 1 to infinity ak cos kx cos nx plus bk sin kx cos nx, right? Then I integrate from minus pi to pi, and remember I can integrate term wise, so I just integrated minus pi to pi dx dx dx, and here also using the fact that I'm assuming that this is uniformly convergent, I can integrate term wise. Now when I integrate this integral, we already know this is 0, right, because cos kx, as we have earlier जो हमने किया था, plus now take this integral. I have got, now look at this integral here. So I've got minus pi to pi cos kx cos nx. Now I'm saying this integral here. Of course, k runs from 1, 2, 3, 4 up to n. Similarly, I have another integral minus pi to pi cos kx, sorry, it's sine kx and cos of nx dx. Now these two integrals are involved here. But if I look at the formulas that we talked about earlier, right? What is this? Cos kx cos nx dx. Cos kx cos nx is equal to 0. This integral is equal to 0 if k is not equal to n, right? And this is equal to pi if, oh sorry, it's equal to 0 if k is not equal to n, and in case k is equal to n, this is equal to pi for n running from 1 to so on and so forth, right? Whatever you, अगर k n के बराबर है तो k भी 1 है, n भी 1 है. So this would be either 0 or pi. But another integral is cos kx sin nx. This is always 0, whatever k and n. So these all terms are going to be 0. Now this thing is all this summation, the contribution to the sum from the sin kx cos nx terms would be 0. So finished. So this is also 0. What we are left with, it would be 0 in case k is not equal to n. The only term would be left where k is equal to n. In that case, I would get a pi. So I would get the only term remaining would be when k is equal to n. So on the right hand side, the only term remaining would be an minus pi to pi cos nx dx, which we know that it is equal to pi. So it would be an into pi, right? So I would get now, so what I have is this minus pi to pi f of x cos nx dx is equal to this thing for all n running from 1 to so on and so forth. So that means an, the coefficient, should be equal to 1 by pi integral from minus pi to pi fx cos nx dx. Now to evaluate bn's, we can again use the trigonometric relations, and we can just multiply throughout by sine nx and get that bn is equal to 1 by pi integral minus pi to pi f of x multiplied by sine nx dx. Now, so of course I have already shown that of course n runs from 1, 2, so on and so forth, and this we did earlier. You can do it yourself. No, it's nothing. The way we did it in cos for ans, you can also find bns. So this is where we have got. अभी तक हम यहाँ पहुँचे. And of course a naught, we also evaluated a naught. What was a naught? A naught is equal to just a naught is 1 by pi minus pi to pi fx dx. So far, where we have reached, we have assumed that this series of trigonometric functions converges. You suppose it did converge uniformly on minus pi to pi, then what should be the relationship of this fx with these unknowns ans, bns, and a naught? And these are the relations that we got with the help of known trigonometric functions. So let me stop here.